So we have seen in the lecture 2 how to achieve sustainable process design through process intensification. But as I said, process intensification is not the only way to achieve this. There are other ways, and we will talk about some other ways to achieve this, and that can be hybrid and other schemes. And just to remind that we are focusing more on energy because energy has been identified in industrial processes that we should make the processes more energy efficient. And so that's why we are looking for processes where we can improve the energy consumption. And as we talked about before, which are those target processes then? The commodity chemical processes are energy intensive, so we can look at them. If we are looking at biopharma processes, they are not really energy intensive, but water intensive and unused material and waste. But some food and health products can also be energy intensive. For example, the meat production involves a lot of energy. So how can we reduce the energy required for meat production? Farming combined with meat production, that is a big issue that needs to be resolved. So what we did also is that we looked at papers published in the last 5 years related to sustainability and related to how many of those papers covered which topics like energy, water, environment, food, economics, others, and whether there were papers that were directly saying out of the 17 sustainable goals, which of them they satisfied. Unfortunately, I could not find a single paper that said this sustainable goal is what we have achieved. So I think we need to direct people that when they talk about their sustainable solutions and so on, they need to tell us which sustainable goal they are satisfying. But what we found is there's quite a lot of paper on CO2 related capture utilization and quite a lot of paper on processing route development and process alternatives that are supposed all to be sustainable. So one can see which direction things are going. Also, like bioethanol and things like that, they don't really reduce the energy problem. So it's another way of getting of transportation fuel. So they're not satisfying the energy efficiency related issues. Only the ones that I've highlighted solve the energy efficiency related problems. Also, we looked at if we captured the CO2 and then converted the CO2 into some chemicals, and you can see the chemicals diethyl ether, dimethyl ether, dimethyl carbonate, methanol, acetic acid, formic acid, succinic acid, for which you will find processes. How much of the CO2 captured will make any impression? It was very disappointing that if we want to produce all the dimethyl ether that is needed at this point on Earth, the CO2 needed for that is equivalent to 35 power plants. That means the CO2 coming out of 35 power plants, if we convert those CO2 into dimethyl ether, we will satisfy the world demand. And then you can see for the other ones, it's less than 10. Surely there are more than 100 power plants on Earth. So this is a problem that unless we increase the use of these kind of chemicals and make them block chemicals, we will not reduce the carbon footprint or the CO2 emission by just converting to some useful chemicals. So that was quite disappointing. And then we looked at which are the unit operations that can be found in chemical processes that use the most energy. Obviously, all the vapor liquid systems will have high energy consumption, and based on energy consumption, they are shown. Distillation is highest, followed by drying, evaporation, extraction, and so on. And then this is very important. Out of the distillation, which are the most energy consuming distillation columns? And we see that these are the hydrocarbon separations, not because they are difficult separations, but because of the volume. The azeotropic separations are very low in the energy consumption column. So if we want to really make a difference, we have to see how to reduce the energy consumption for the hydrocarbon columns rather than doing azeotropic separation with solvents or even without solvents, because they will not change the carbon footprint that much because the volume is much lower. They're interesting problems, scientific interesting problems, but the one that will change, make a big impact significantly are the columns that use a lot of energy because of their volume. And some of them are difficult, like propane, propylene, ethane, ethylene. Those are difficult separations, as well as the volume is large. So this first example, I will not go through it. We have already talked about it. When we do this kind of examples, we need to see how much energy they use and how much potentially the energy we can save through this. If it is a difficult problem, interesting problem, but do not use that much energy, there's no point in trying to do a PI for that. We need to see whether the energy reduced, even if it is 20%, it's significant. 20% out of 10 and 20% out of 1,000 is a different number. So we need to see how much is the energy consumption. And so if we take a hydrocarbon separation, it's actually 4 distillation columns. And we find out that the last 2 columns use quite a lot of energy because the driving force for their separation is quite small. So the smaller the driving force, the bigger is the energy required. How can we help to reduce the energy? We can look at the long-term solution. Can we replace totally the distillation column? We can if the corresponding material for membrane for adsorption is found. But how long do we have to wait for that? I don't see within the next 10 or 15 years somebody coming out with a membrane or adsorption that can totally replace the distillation columns at the size that we require, not the laboratory size. So what is the short-term solution? Should we wait 10 or 20 years until somebody comes with the membrane? Or should we do something now? So that is the short-term solution, where we keep the distillation as it is, but we add a membrane unit, a very small membrane unit for which the membrane already exists, and we can save quite a lot of energy. So the rule for combining not just membrane, another non-energy intensive process, if we want to make a hybrid of this, we combine 2 types of techniques such that each operate at its highest efficiency. So the distillation will operate at its highest efficiency. The membrane or adsorption will operate at its highest efficiency. The combined will be giving us between 10 to 50% saving. And then if you think that just in USA, I think No, I think this 100,000 is for the world. If there are at least 100,000 distillation columns operating on Earth, and we can save between 10 to 50% of their energy, that can be a very significant impact. And as engineers, we can try to influence the decision makers to go for this. And I will give you more details on this afterwards, how to do those calculations. So just the distillation column and membrane is not the only solution. We can also have dividing wall column solutions, which when we want to simulate is a Petliuk column on the right. So a dividing wall column can also save some energy, but we have to be sure that the criteria for using a dividing wall column is satisfied. Not every 3-compound separation will be good for dividing wall column. Only some of them will be good. So here is an example. We have another 5-compound mixture, and we have 4 distillation columns, and we have optimized it with respect to energy requirement. Can we do further? Yes, we can do by putting membranes, and you will see afterwards how we do that. But we can also do dividing wall column. We can take the first 2 and combine them together into a dividing wall column. In simulation, it looks 2 columns like in the Petliuk column, but actual is 1 column. And then we have the 2 other columns. And for the last column, we also put a membrane unit. And you will see why adding a membrane unit to the top product can help. So that's one combination that definitely will give better solution than the one we had original. And another could be, we have 4 columns. So can we combine? How many dividing wall column combinations can we do? We can take the first 2. We can take the middle 2. We can take the last 2. The middle 2, taking the middle 2 does not help, because as I said, the compounds and the purity and the flow rate, they all are important in configuring distillation columns. So the middle 2 are not very interesting, but the first 2 and the last 2 can be combined, which also becomes interesting. So this kind of alternatives can easily be generated and also be verified through simulation. So there is no intensification here in the way that we talked about in terms of phenomena, but we can go directly to dividing wall column as long as our rules for combining the columns into a dividing wall column is satisfied. Because the 2 columns are combined together in a dividing wall column, you can see that there is no product going out of the first column. The feed is coming to the first column, and the top and bottom product go to the second column, and from the top and bottom product, some vapor and liquid go back to the first column, and all the products are coming out from the second column. That's a typical Petliuk column combination. And so in the second column, there are more stages than the first column to account for the stages above the dividing wall section and below the dividing wall section. So this can be configured, and it's not that easy to simulate them because the flow rates between the columns are very sensitive. But one can find the solution. And so an important question with these columns is the operability and control. That needs to be looked at in more detail. And people are doing that. And then the next is that if we have a process and we have done the heat integration of the process, so by doing the heat integration, we minimize the utilities required for heating and cooling. So without integration, we would need much more heating and cooling. Because of integration of streams that needs to be heated with streams that needs to be cooled, we can reduce that. And also when we do a process optimization, the process optimization changes the temperature pressure of the streams, and based on that, the energy demand changes. So normal way of doing this kind of problem is to sequentially do it. We simulate the process, we do the heat integration, find out the minimum utilities, and then based on that minimum utilities, we calculate other costs by optimization. And that's the sequential way of solving the integration and optimization. But Duran-Grossman paper from 1986 proposed that this can be combined together in such a way that after the flow sheet is simulated, let's say the optimizer gives us design variables, then with those design variables, the flow sheet is simulated based on the temperature, pressure, and the duties. The heat integration module calculates the utilities, and based on that, those utilities, together with all the process simulations, are used to get the new design variables. So what you see as heat integration module, the calculation of that is put as a utility calculator to the process simulator. So when the process simulator is calculating the objective function, it actually goes to the utility calculator to calculate the minimum utilities required. And then based on that, the optimizer then tells what are the new design variables. The simulators don't come with that utility calculator. We have developed our one based on Duran-Grossman work. So that is a tool that you need to add to your simulator, and then you would be able to do simultaneous heat integration and optimization. And these results will be shown later. Then the question of integrated networks. We talked about that we have a process and we have a boundary, and the process will give us chemicals, and it will also impact the environment because there will be CO2 coming out directly. And also, if we have a power plant giving supplying the energy that is required by the process, that power plant will also be releasing CO2. So we have a direct CO2 emission and an indirect CO2 emission. And so the question is, where is the real boundary of the system? We have to always be careful that we take into account both the direct and the indirect. And we can also talk about classifying these kind of processes. The chemical process is an energy demanding technology. We need energy to run that chemical process, just as we need energy to run cars, airplanes, etc. And then there is energy producing technologies like power plants, dams, windmills, etc. They produce the technology that we need. And the energy demanding technologies may give direct CO2 emission like cars, airplanes. Not all chemical processes, but most of them. The energy producing technologies indirectly give also emit CO2, but they provide the energy that we need. So then the idea is, can we combine them in such a way that we capture the CO2 that we can convert and utilize, and the remaining CO2 we don't take from a power plant, which will have indirect CO2 emission, but take from other energy source, solar, wind, nuclear, that will not emit energy, CO2. And then can we find out a combination of different sources that will give us zero CO2 emission? I think that's a very interesting topic, and I will show you two examples. So let's take the flue gas or waste gas, which has CO2. We capture the CO2, we take it into the process, and we produce chemicals. So here, this is the energy demanding process, but we need to combine with the energy producing technologies, and the energy producing technologies should not emit CO2. And a good example for that, I will show here. So here is the process. When we want to do this simulation, design, synthesis, innovation, we are making two very important assumptions. We assume that all the energy we need are available, all the water we need are available, and we waste water and we waste energy. So we assume that there is no limit of the energy we need and the water we need. But we could put a limit, and we could put what kind of energy we will use, what kind of water we will use. And then we could also say that not only this, we'll put a limit, we will also synthesize the network for energy, for water. And then we can say that this network of energy, water, process, this will be our total system. Can we find an optimal solution that will have net CO2 negative, and it is safe and healthy and operable? You can unfortunately not see the bottom one. We have actually make a case study with location in China and with my collaborators in China who have solved this problem. And we can say that a combination of coal-based power plant and solar and water, and using the captured CO2, we will produce some chemical that we can sell, and it is profitable and it is net CO2 negative. So this can be done. And I hope more and more solutions like that will come up. Now let's go back to the distillation, where I will show you very briefly how the hybrid systems distillation with membrane can be obtained. I've talked about this, so let's skip. So now we are talking about that if we want to combine distillation with membrane into a hybrid, distillation must operate at its highest efficiency and membrane must operate at its highest efficiency. On the curve that you see is that as we go along with purity, the higher purity product we want, the reboiler duty increases. So distillation cannot be that efficient if we want very high purity product. So we see that up to a certain point, distillation is the best. You cannot replace it with anything else. But after a certain purity, the amount of energy required is very high. So nearly 80% of the energy is used in the inefficient part. So then the question is, why should we use distillation for that inefficient part? Can we replace it with something else? And that something else, one of the alternatives could be membrane. There are other alternatives. So we combine membrane with distillation in such that the membrane is efficient for its part, distillation is efficient for its part. Now, when we talk about the membrane, you will think that the membrane should take the two compounds, let's say the light and the heavy, and the permeate will be the light compound going from, let's say, 95% to 99%. That would be the typical thing that people would think of, but that's not what we are talking about. Membrane is efficient only when the flux is small. And if you take 95% of the light product, the flux of that compound is high. What we want to do is to use the membrane to take the impurity, the other compound, compound B, which is in, let's say, 5%. So the more compound we remove compound B, the more pure the A will become. And that is what we want to do with the membrane. So it's the opposite way of using the membrane. So we remove the impurity with the membrane. And by definition, the compound we want becomes higher pure. And if we do that for a real system, we do the simulation, we do the energy analysis, we find out that the last column uses a lot of energy because the driving force is small. The second column is high because of the flow rate, and the third column, the driving force is very low, so the energy is quite high. So we can target then the second, the third and the fourth columns. And the driving forces are this. They look big, but compared to the first and second, they are quite small. So that's the maximum. Based on the driving force, we now know what kind of column design should be. And then we find out that for column 4, let me go back. Okay, for column 4, the blue curve, what we call cutoff is that after the cutoff point at the small 85%, we will not use distillation. And at the last point, we want to achieve that composition with some other unit. And for the second one, we want to cut off at 0.9, and we still want to go to the high purity. And you can see that the blue one has a lower reboiler duty than the green one, because the green one has a lower driving force, so it needs more energy. And the blue one has higher driving force, so it needs less energy. So they're directly related to the driving force. Then we can calculate out very easily from the values that we have on this graph how much energy we would be saving potentially. And we see that for the column 4, we can save 44%, and for the next column, 39%. Then we put the membrane units. We look for membranes. We have found membranes that can do these separations, and we calculate and we find the savings. And then we calculate the membrane area and so on, based on real membrane data. And then we find out, based on the savings on energy and additional profit, how long it will take to pay back for the membrane. For the first column, very little. For the second column, because the permeability was not very high, it needs a little bit longer. So that's the solution that can be done quite easily. I will show you a demonstration afterwards. So based on the established workflows for generating the hybrid skins, we developed the options for steps 10 to 12 in ProCFD. Then links to external tools, process simulators, control toolbox, monitoring, etc. are being considered. The objective is to obtain truly innovative and sustainable solutions that are reliable and satisfy the nexus challenge of energy, water, food, environment. ProCFD and the collection of interlinked tools help to solve problems fast, efficiently, and reliably. So in the next presentation, you will see heat integration step, that is step 10 in ProCFD. Other tools also have heat integration. We will just show our one. Heat integration and optimization for further improvement that will be demonstrated with Pro 2. Simultaneous heat integration and process optimization through the PSE for speed module connected to Pro 2. And finally, I will show you with Excel-based prototypes the hybrid separation and the reactive distillation. So with that, I end. If you have any questions, we will take them before we go to the next. Are there questions?
Yes. Can you give an example in which case the dividing wall column will not work?
One of those criteria is that the top product in the dividing wall column needs to have sufficiently large flow rate. If that compound is not present in large amount, then there is not enough vapor flow rate to go back and forth, and then the dividing wall column will not work. So composition is very important. Also, the pressure requirement. In a dividing wall column, we cannot have different pressures in the two sections. And if pressure drop is needed or different pressures are needed, because of the compounds that we are separating, that is not possible. So very quickly, these are two that we know very well. It doesn't matter what the middle compound flow rate is, but the top compound and the bottom compound flow rate needs to be sufficiently large. Okay.
Another one is, can you place the multiscale China case study reference?
Oh, yes. Let me go to the slide. Here it is. It was published in 2020. I think if you look for Lee et al., that is Lee, and then Ghani, I'm the last author, Computers and Chemical Engineering 2020, you will find the paper. It is also listed at the end in the list of references. And now we have solved this problem with uncertainty included in it also. Okay. Otherwise, send me an email and I will send you the paper. Any more questions?
There's no any questions now.
Okay. Then I will stop here and Jakrapat and Konkanak will take over.